We present detection of typical landmarks for osteoporosis pre-screening in dental panoramic radiographs. As one of the most common bone diseases, osteoporosis has affected millions of people every year. The DXA scan is typically used to measure bone mineral density and diagnose osteoporosis. However, this approach is relatively expensive. On the other hand, dental panoramic radiographs draw extensive attention, owing to its availability and promising results for the potential of pre-screening. Furthermore, the accuracy can be improved when only using 8 image patches around special landmarks. This is due to the fact that the features around such landmarks are discriminative and the noisy background is ignored. But nonetheless, to extract features, such methods heavily rely on the manual annotations of typical landmarks, as shown in Figure 1b, which severely limits its practical application. In this work, we aim to address this problem by proposing automatic detection of typical landmarks. We utilize a dataset of 108 DPR images extracted from different subjects for typical landmark detection. The image comes from 52 subjects with osteoporosis and 56 normal subjects. For each DPR image, 8 landmarks correlated with the osteoporosis condition are manually labeled by dentists. Then, our task is to localize those landmarks automatically. Motivated by the huge success of convolutional neural network in general object detection, one natural solution is to directly apply a popular deep detector to localize those typical landmarks. For a practical osteoporosis pre-screening system, the detector should be given consideration to both accuracy and efficiency. So we use RetinaNet. It's an efficient single-stage deep learning detector. Here, we modified the RetinaNet and added a smaller anchor to capture tiny features. During training, the targets are 8 bounding boxes centered around the 8 landmarks. During inference, the outputs of the detection network are bounding boxes with predict labels, but we only need landmark coordinates. So here we propose 2 approaches to convert bounding boxes into the coordinates: the global detection and the local detection. In global detection, coordinates of each landmark are the center of the bounding box with the highest confidence score over the whole image, such as this one. However, the wrong detection outliers with a high score here will lead to wrong inference. So we propose another conversion method called local detection. The searching range is limited within the scope where all training samples with same landmark label lie within this area, and thus we can filter outliers and get better results. Nonetheless, we observe that the CN detectors fail to separate targets with similar intensity and text features. Therefore, we use RetinaNet as a baseline and present a static shape model for typical landmark detection. Our method can exploit the prior spatial distribution of landmarks and their structural relationship. It consists of shape model and appearance model. According to the feature extraction area, there are a holistic appearance model and a patch-based appearance model. For shape model, generalized precrusty analysis and the principal component analysis are used to get the orthonormal shape basis US. With this US, we can reconstruct the shape instance SI with this equation. Here, P is the shape parameters. Afterwards, to take advantage of texture and intensity features, we also construct an appearance model. Each DPR image is warped into the main shape S-bar and generates the shape-normalized DPR image, where W is the warping function, and after PCA is used to construct the orthonormal appearance spaces UA. Here F is the feature function such as shift or LBP. And thus, we can construct appearance instance using this equation. The fitting procedure tries to recover parameterized description of a test sample. It's an optimization with respect to the shape appearance and the appearance parameters. Shape parameters is P and the appearance parameters is C. With the best fitting parameters, we can determine the landmark shape as hat and the coordinates of the test sample. The task is to localize the typical landmarks in osteoporosis datasets. The loss is the normalized sum of squared difference between the predicted landmark S and the ground truth landmark S star. Here NS star is the normalized factor. The deep learning model, RetinaNet, outputs bounding boxes. For fair comparison, we use the aforementioned global detection or local detection to convert such bounding boxes into landmarks. Static shape model uses shift features and outputs coordinates directly. For each method, we adopt five-fold cross-validation. For static shape model, we shrink 10% on each side to contain all landmarks and remove unrelated background. Table 1 enumerates the experiment results. We can say that local detection results outperforms global detection for most cases. This could be due to the fact that the typical landmarks lie within a certain range of DPR image that can be estimated by the spatial distribution in that training set. And thus, more potential landmark candidates can be selected rather than outliers lying far from the ground truth landmark. For static shape model, the patch-based model ignores background noises and is more robust in case of limited datasets. We can say that the patch-based static shape model outperforms all the other methods by a significant margin and achieves the lowest loss. This demonstrates the generalization capability and effectiveness of the proposed method. Besides, we observe that the displacement of static shape model prediction is much smaller than the RetinaNet, as illustrated in this figure, which is partially because static shape model take use of spatial relationship between landmarks. Thanks for watching. I'm happy to answer questions.